Gators, we're going to be confirming continuity over an interval and removing discontinuities. Finding the domain. There are three scenarios to watch for when looking for a restriction on the domain, and the first one is denominators. Remember, in a rational expression, the denominator cannot be equal to 0. So that means that there will be a restriction in that x cannot equal -1 on the domain. Another one is even roots. Under a square root, fourth root, or sixth root, the argument, the expression under the root, has to be greater or equal to 0. So in this case, x has to be greater or equal to -3/7. For a cube root, we are allowed to put a negative number, and a negative number comes out. It's only even roots that we need to be alerted about. In logarithms, remember what a logarithm looks like. It is the inverse of an exponential, and the domain is positive. So this argument right here has to be greater than 0. So 2x has to be greater than -1, or x has to be greater than -1/2 in the domain. So keeping these in mind, let's go through some examples. This is a rational expression, so we look at the denominator. X cannot equal to 0. So our domain is all real numbers, but x cannot equal to 0. In interval notation, it will be -∞ to 0 union 0 to infinity. This is a rational expression. Again, we've got to look at the denominator. X cannot equal 0, but there's a square root, and we know that the argument has to be greater or equal to 0. So x is greater or equal to -5. So putting this together, these two requirements together, x has to be greater or equal to -5, but x is not allowed to be equal to 0. Or we can write it in interval notation, -5 to 0 union 0 to infinity. Over here we have a rational expression. 2 minus root x is the denominator, and that cannot equal 0. 2 cannot equal root x, and so 4 cannot equal x. The other situation is x, what's under the square root, has to be greater or equal to 0. So we have these two requirements right here, that x cannot equal to 4 and that x has to be greater or equal to 0. So the domain can be written as x greater or equal to 0, x cannot equal 4. Or it will be from 0 to 4 union 4 to infinity. Let's take a look at our natural logarithm. Our denominator dictates that we cannot equal 0, so right off the bat, x cannot equal 4. We know that the argument has to be positive, and the only way it's going to be positive is if the numerator is positive and the denominator is positive, and that'll happen when x is greater than 4. As long as it's just a little greater than 4, that'll be a positive number, and of course anything greater than 4 is positive. The other scenario is negative over negative, and if we have a negative number in the numerator and a negative number in the denominator, this will be greater than 0, and that happens when x is greater than 0. Greater or greater than 0, right? We can't let it equal 0 because we have this restriction of it has to be greater than 0. So we have this requirement, and this requirement. So we say the domain is x is greater than 4, it can't equal 4, and x is greater than 0. Oh, I'm sorry, this is not true. It's not greater than 0. It is, in order for me to have a negative, x will have to be less than 0, because when it's at less than 0, this will be a negative, and less than 0, this will be a negative. So this is the requirement. This requirement, this one, and this one. So our domain is x is less than 0, and x is greater than 4. We don't have to put the not equal to 4 because this already says that. Or we're going to go from -∞ to 0 union 4 to infinity. So there's a gap here where there's some x values that we cannot have. Where is the function continuous? This is the question is not asking for the domain, it's asking where is it continuous. We can see this is a polynomial, so it's continuous. Actually, there's a value everywhere. What the question is it continuous? So we need to take a look at the limit as x approaches 0 from the left and the right. From the left, the answer will be -1/7. And from the right, if I put 0 in here, it'll be -3/7. So clearly these limits are not the same. So we know that it's discontinuous at x equal to 0. Now let's look at this branch. This branch, x cannot equal 7 because that's the denominator. But I'm looking right here, and I'm really, for this expression, I'm only looking from 0 to 3. So this is not required. I'm never going to have 7 in this domain, so I don't have to worry about that. Now this denominator, x, cannot equal 5. So here's another point of discontinuity. X is equal to 5. So we have those two places at 0, and we have at 5. We need to now check out the limit at 3. Let's go ahead. Let me do another color so I know I'm doing that. Okay, so at 3, I'm going to put 3 in here. This will be 3 over -4. And now I'm going to check the right-hand side, and that'll be 21 take away 15 all over 12 take away 20. And that's -6 or 6 over -8, which is the same as this one. So 3 is okay. 3 is not a point of discontinuity. Instead they hook up right here. So now I'm ready to write where is the function continuous from -infinity to 0, union 0 to 5, union 5 to infinity. What is removable discontinuity? Removable discontinuity occurs when a limit exists, but the limit does not equal the value of the function. Let's take a look at this example right here. F of x is equal to a line with a hole in it. And we can see right here, this is where the hole is. The hole is at x is equal to 1. The question is, what is that y value for the hole? And the y value at the hole, we're trying to approach 1 from the left side, and we want to make sure we find 1 from the right-hand side of f of x. We want to see what it equals. So as we remember that this is the line x plus 1, so we're looking at the limit as x approaches 1 of x plus 1. So we're actually looking at this limit because this is going to be reduced when we come over here to look at the limit. So using substitution, as x approaches 1, the y value will be equal to 2. So this point right here will be the point 1, 2. As we get close to 1 from the left-hand side and from the right-hand side, it's getting close to the number 2. If the function is continuous, that means there's a value for everyone, and it's like one continuous, drawing of a pen where there's no breaks. What we would like to do is we would like to take this function. This function is true only when x does not equal -4. We would like to see the filled in. There's a hole in there, and we would like to see how it would filled in. So this function, you can see that there's a hole. The hole occurs at 4. So what we're trying to do is we're trying to take the limit as x approaches -4 of f of x. And when we do that, we're going to reduce this. And so what we're looking at is the limit as x approaches -4 of x plus 2. And we'll just do simple substitution, and that's -2. So this is the point that we're filling in to make this continuous, and now this will be continuous. Let the function f be defined by this. You can see this is a rational expression, but x cannot equal 6, and we want to make it continuous. So what will the y value be at 6 so that we can fill in the hole? And so here's our limit. Again, here's where the hole occurs. And if we reduce here, and then we can just substitute 6 into the actual line, and the answer will be 9. So for what value of a? Well, we want a to be the number 9. That'll fill in the hole for the removable discontinuity. Use these piecewise functions to find the following without the calculator. Okay, so we're going to approach 0 from the left-hand side. That's this. And so the answer will be -2. And now we're going to do it from the right-hand side, and that'll be 2. And this limit does not exist. The two-sided limit does not exist. So give the intervals where f is continuous. We know it's not continuous at 0, so it goes from -infinity to 0, union 0 to infinity. Let's take a look at this piecewise function. As we approach 2 from the left-hand side, it looks like it's going to be 3 times 2 squared minus 2. That's 12, take away 2, which is 10. Now let's do the right-hand side of 2. And so that'll be 2 times 2 plus 6. And that is going to be a 10. It looks like on the left side it's 10, on the right side is 10. So the limit is 10. Now, what's the limit of g of x as x approaches 0? X approaches 0 is located in this piecewise function, less than 2. So put a 0 in, and the answer is 0. List the intervals where g is continuous. So it looks like it's continuous everywhere. So it's from -infinity to infinity. So we have a point, and there's no breaks. If f of x is continuous, a function is shown, find the value of the unknown a. So right here, as x is greater than 2, what must this y value be? So in order for that to happen, the left-sided limit and the right-sided limit must be equal to each other. On the left side, we're going to put 2 right here. That'll be a 4. And in order for them to be equal to each other, that limit must also be 4. So this value here must be the number 4 for that to happen. And that's the end of the screencast.